Today's section is 3.2 on logarithmic functions and their graphs. So there's a relationship between exponential functions and logarithmic functions. And so I'm going to kind of start out with a YouTube video here to explain what a logarithm is. And then we're going to talk about how the exponentials and logarithms are related, and then do a little bit of math with them. So hang tight and watch this video coming up.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases, extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 to 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Okay, so that video explained some of the relationship between logs and exponential functions. So one of the relationships it tried to exemplify here was log base a of x equals y has this relationship to exponentials. Okay, so again, make sure you understand the way we say this. If the a is subscript, which means lower, it's log base a of x equals y. And in order to make that an exponential, you say a to the y equals x. And so if you write it down like this, it just follows that format. A to the y equals x. Okay, so this exponential can be written as this log, and this log can be written as this exponential, and they are equivalent expressions. And that helps us solve different log problems or different exponential problems, depending on which way we're going. Okay, so let's see. Just a few examples here. In my opinion, it's much easier to go from logarithmic to exponential than the other way around. But just a couple quick examples here. 3 raised to the 5th power equals W, and that's what's written here. And if I have this one, it's definitely much more difficult to go backwards. Here's kind of the way I think about it, okay? So it always equals the power. So notice that the power is here and the power is all alone. So in this case, if I say this expression, x squared, x is what's called the base. So that helps me remember that it's going to be log base x of 9 equals the power. Okay, so it's the base of whatever is over here by itself equals the power. And so you can kind of go back and forth doing it that way. Okay, so in this case right here, change 3 to the 5th equals 243 to logarithmic form. Remember that it's the log base 3 of this side equals the power. Okay, so the power is going to go by itself. And for me, I always double check just to make sure I got it right. This way is easier. 3 to the 5th equals 243. Okay, so it's much easier to think about it that way. Go ahead and try the next one. So hit pause real quick. Try the next one and see if you can convert it to logarithmic form. Okay, so there's a lot going on this one, but again, just to keep it kind of basic, here's your base. So it's going to be log base 5 of this side. So m over n equals the power, which is negative 2x. Okay, so again, it follows the same format. In order to change it to exponential form, I think, again, this one is much, much easier. It's the base raised to this power equals this number. So 3 to the 4th equals 81. Same thing, go ahead and pause the video right now, try the next one, and see what you get. Here's the base raised to that power equals this one right there. So this one would be 4 raised to the 5 minus x equals p. Okay, so that one's a little bit different because the exponent is 5 minus x, but same thing. When it asks you to evaluate like this, basically there's kind of something I do to help me here. It says evaluate log base 9 of 3. We're going to see how to do these on the calculator later, which makes this kind of insignificant. However, if it wants you to evaluate without using the calculator, what I would do is I would say, I don't know what that equals, so I'm going to put equals question mark. And it's in logarithmic form right now, and if I change it to exponential, maybe I can make sense of this. So there's your base raised to this power equals this. So it'd be 9 raised to what power equals 3. So this one's kind of a tough one. If it was 3 to what power equals 9, that's an easy one. You square 3. But this one is getting smaller. 9 to what power equals 3. So hopefully you know that if the question mark is a half, it means you take the square root. Okay, so in this case, it would be a half. That would be the answer to log base 9 of 3 would be a half. Okay, so there's some properties here. You can verify this by changing it to exponential form. I'm not going to verify all these, but they are kind of nice to know things. They shorten up some problems sometimes. But with the amount of practice we're going to get going back and forth between logarithmic and exponential, some of these should be just kind of obvious. So for example, if I wanted to change this one from logarithmic to exponential, it'd be a to the 0 equals 1. So hopefully that makes sense. Anything raised to the 0 power equals 1. If I change this one, it'd be a to the 1 equals a. Okay, so they're helpful. Again, they shorten up some things, but hopefully you can make sense of the problem even not knowing these by heart. Okay, so there's something called a common log. Just like in the video you watched earlier, common logs have what's called a base 10. So this is the one on your calculator. It just says log. If it just says log without any subscript, it's assumed that you know that it's base 10. It's the same thing as if I write x. It's assumed that you know that it's 1x. We don't write the 1. Same thing as I don't write the base 10 all the time. Sometimes I do, sometimes I don't. But usually it's just implied that it's base 10. So base 10 is most common on calculators. And then we also have what's called the natural log. So I know it says ln, not nl, like you would think for natural, but ln x is the abbreviation for natural log of x. So that's this using the function e. Okay, so e again is really important in calculus. And so being able to undo exponentials with e is really important for recalculus. So natural log of x is the same as log base e to the x. Those are two equivalent statements, so it means that it has a base e. So the natural log has base e. So that's kind of the gist of that. And also it does have its own button on the calculator also. So let me just go ahead and show you that. Right here is the LOG key. So let me see if I can make this bigger. LOG is right, maybe. It's not going to let me draw. Nope. So LOG is to the left of the 7. And then LN is right below it. It's to the left of the 4. So hopefully you guys can see those keys. Okay. So next, it's just asking me to evaluate a couple of things. These are purely calculator problems for the most part. Okay. So the first one is, I guess, and the second one isn't. So again, if it's asking me to evaluate these, you can kind of make sense of them by changing them from one form to the other. So this one here, I would put equals question mark. Okay, and then I would change it from exponential to logarithmic. So remember that this is your base. So it'd be log base 10 of question mark equals log of 7. Okay, so it's log base 10 of this, of the question mark, equals your exponent. It's implied that there's a 10 here. So what do you think the question mark equals? I think it's going to be 7. And you can verify that by plugging it in the calculator also. Okay. This one is a little bit trickier. So this one doesn't happen very often. But one of the rules of exponents, I hope you remember, is that if you have like x squared times, let's see, x to the 6th, remember that you would add those exponents. That's the same thing as x to the 2 plus 6, which would be x to the 8th. So if you have this addition, I can actually split it backwards into the multiplication. So to make sense of this one, I am going to split it into the multiplication. So it'd be e to the first times e to the ln natural log of 5. Okay, so e to the first is just e, so that one's kind of the easy one. And then to evaluate this, we would say e to the natural log of 5 equals question mark. So this is your, e is your base. So we're going to take e to the question mark equals natural log of 5. All right. So in order to think about that one, actually, in order to do this one, I kind of went too far on this one. In order to do this one by hand, let's just go ahead and plug this into the calculator right there. So that's a much easier way to do it. This part is e, and then the second part would be e raised to the natural log of 5. So let me go ahead and type that in. So if I hit second natural log here, okay, so let's try this again. Second, and then the natural log key says e to the, and then natural log of 5, and then hit enter, and that's just 5, okay? So this would be e, this would be 5, so that would be 5e is the simplified version. Okay, so some of these can be done by hand. Some of them I want you to do on the calculator. And yeah, that's kind of it for those two examples. So next page here, solving logarithmic equations. So we're going to get lots of different ways to do this. The first way we're going to do it, you can see that the log base 3 is the same as the log base 3 on this side. That means that these pieces also must be the same. So we're going to get ways, more and more complicated ways to solve these. For right now, we're just going to keep it easy. If the bases are the same, you just take this part and you set them equal to each other. That's it. So it'd be x plus 1 equals 2x minus 3. And then you go ahead and solve this. and you get 5 equals x, okay? So that one right there should be pretty much a gimme on the test. If the bases are the same, go ahead and set the what's in the parentheses equal to each other and solve. Let's see. I added 4. I should have added 3. I guess it should be a gimme, and I just missed it. So make sure your arithmetic is right, and then it should be a gimme. So x equals 4. There we go. That's better. All right, so the next thing I want to talk about is you saw that there's a relationship between the equations of logarithmic and exponential functions. There's also a relationship in the graphs. So in the last section, 3.1, we graphed these exponentials. And so that right there would be an exponential function. So remember that it has that 0.01 that's really important, and it starts out slow and then really bends up with that exponential growth. Notice that this guy right here is the natural log function, or the logarithmic function. So it's going to start off very, very steep, and then it's going to level out like this. And if you guys can see that this line right here is y equals x. If you can see that these are reflections of each other, okay? So over that line, y equals x, all those points match up. So visually, I can tell the relationship between exponential functions and logarithmic functions because they're reflections of each other over the graph. So that would be a visual check to see what logarithmic functions look like. So exponential functions, again, this is the growth of a virus. This is hopefully your money in the stock market. What has like logarithmic growth? Well, think about like human growth. When you're a little kid or a baby, you grow rapidly, 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 and then when you're a teenager, you start slowing down. So it's not exactly logarithmic growth, because logarithmic, you would keep increasing your height forever. But it does slow down, slow down, slow down, and you don't get much taller. So that would maybe be something. Height of a tree, same thing. If you think about a seedling, tree seedling, it grows very, very, very rapidly, and then it's all of a sudden when it reaches its eventual height, it's going to slow down, and not grow much over the years. Okay, so the domain and range of log functions. So if I'm looking at this function right here, domain going from left to right, it goes from 0 to infinity. Okay, so it's the y-axis is your asymptote here, so it's going to go from 0 to infinity. Range, any value, negative or positive, so it's negative infinity to infinity. And remember that that is the reverse of the exponential function, okay? So that would be the domain and range of log functions. So this question right here, find the domain, vertical asymptote, and x-intercept of that graph. So a couple things about this. It's basically getting you to think about the shifts and stretches and compressions of functions. So just remember our rules that we had. If you have a plus or minus to x, it moves it left and right. So in this case, I do have x minus 3. So remember, that's the one that's opposite of what it looks like. So your normal log function, which remember looks like this, okay, is going to move to the right 3. So that ordered pair that was right here, which I guess we didn't really discuss a lot up here. On this graph, we've discussed that 0, 1 is really important. That means if it's a reflection, 1, 0 is really important for the logarithmic function. So if I take that ordered pair 1, 0, and I move it to the right 3, okay, that would now be at 4, 0. Okay, so that's important. And then, so that would be our x-intercept. Vertical asymptote would now be, instead of being x equals 0, which is the y-axis, it's going to be to the right 3. So it's going to be x equals 3. I'm going to put VA for vertical asymptote. This is your x-intercept. And the domain would now be 3 over. So it was from 0 to infinity. And since we moved it 3 to the right, it's now going to be 3 to infinity. And again, you'd have this kind of gap back here where there's nothing between 0 and 3. So that would be your vertical asymptote, x-intercept, and the domain. And again, you can graph it and just see what it looks like. So same thing with these other ones, you guys. I'm not going to graph this, but you can see what it does look like. Actually, maybe I should, because to show you how to type it into the calculator. So there's the log base key, which I believe I showed you before. So let's go ahead and take a look at that. This calculator is being tricky today. All right, so go ahead and hit graph. I'm sorry, y equals. And to get log base 4 of x, if I go to math, and it's going to be down in that log base, so I believe it's option A, hit log base, and then it opens up this notation, 4 of x. And then on the outside, I'm going to have plus 2. So think about what that does. That's going to take your normal logarithmic function, and it should shift it up 2. So hopefully when we graph it, we see it shifted up 2. And there we go. So it's our normal curve, but it's shifted up 2. So if I ask you to graph it, just go ahead and type it in using the log base to graph. Okay, so that right there is 3.2 on logarithms.